Log on, tune in, find out. Another good idea from Cambridge.
Let's get started with this next session on design computer experiments. And our first speaker is David Steinberg from Tel Aviv University, and he's going to be talking about orthogonal nearly Latin hypercube designs.
Thank you, Dave. This is in many respects talk that we heard start the morning from Boshin. So, of course, since all of you were up bright and early and here in the rain at 9 o'clock, am I wired or not?
Not turned on.
It's not turned on. Where's the switch?
On the top.
There's a red light.
There it is. Oh, got it. Okay, so I'm going to be talking about nearly Latin hypercube designs, but designs that are orthogonal. So we'll get to that in just a minute. This is joint work with Dennis Lin, and it also includes some ideas from Dietze Burstein, who's a former PhD student of mine. I'm going to talk in about one slide about designing computer experiments. We've heard about that all morning and certainly discussed it before we set out for the break. I don't think much needs to be said there. Latin hypercube designs, we also, by now, all know what they are, so I'm going to go through that very quickly. I'll talk about rotated factorial designs. We heard from Boshin also a bit about things you can achieve with rotation, and so what you didn't understand in his talk, we'll see if you understand it out of my talk by the time you heard from both of us. I hope you will. And then most of the time I'm going to be talking about the orthogonal nearly Latin hypercube designs as designs that you can get from rotated factorial designs. Okay. Why might you want to use designs like this? Again, going back to our discussion, I think the sort of designs that I'm going to talk about are designs that would be most interesting in a screening and useful in a screening type setting. So you have a fairly large number of factors. You want to get some idea which of the factors which really have impact. You'd like to do that with a fairly small number of runs. So if you're thinking of the sort of typical guidelines that have come out on, you want about 10 runs for each factor that you have in the experiment. If you're really interested in doing more intense modeling, I'm interested in situations where the ratio of runs to factors is much, much smaller, and you're really trying to highlight which are the most important factors. Again, I think that those are, in terms of getting orthogonality, insisting on orthogonality in a design, I think those are the settings where orthogonality is likely to be most interesting and most useful. Okay, you know all about Latin hypercube designs, so I'm not going to say anything more about those. The only thing I'm going to mention briefly is just a little bit of the history here. And again, most of you already saw this in Boshin's talk. The first paper that talked about getting orthogonal Latin hypercube designs was the paper by Kenny Yee. And Kenny showed how if you had a design with 2 to the m runs, you could get 2 times m minus 2 completely orthogonal columns, and completely orthogonal in the sense of linearly orthogonal. So the linear main effects are orthogonal to one another. Okay, but you can see that in terms of screening as a ratio, this is not very high unless m is very small, and those aren't the situations that I'm interested in. Then there was the paper, again, which Boshin mentioned, by Neil Butler, which showed how you get some orthogonality with respect to trigonometric regression as opposed to polynomial regression. And there's been a series of papers that have followed up on this and presented different methods to get orthogonality in Latin hypercube designs. And I think the most interesting and certainly the work that's really has carried this forward substantially is the recent work by Devin Lin, and that, of course, is what Boshin reported on this morning. And I'll give a summary of some of those results in just a bit. My own work with Dennis Lin is going to be fundamental to what I'm going to talk about using this talk as well, so I'm going to mention that briefly. And I think what was most interesting about our paper, from a practical standpoint, it solved almost nothing because it covered such a limited number of cases. From a theoretical standpoint, I guess what was interesting in it was that it showed that there are settings in which you could get nearly saturated orthogonal Latin hypercube designs. something which, at least when we first started to look at this, I thought there's no way you could do it. But as you saw in Beauchin's paper, we can, but as I said, it only works for very special cases of n. So practically speaking, it didn't really solve a whole lot. So here are some known results, and they, this is, in most cases, I've tried, in all cases I've tried, in most cases I hope I've succeeded, in citing the original authors who had these results. So my own paper with Dennis Lin is in here only for the 16-run 12-factor design. And then there's some follow-up work by Sun, Liu, and Lin. Both of those are the Dennis Lins. These two are the Devin Lins. And these are the papers that she had with Rahul Mukherjee and Beauchin, and with Derek, Randy Sitter, and Beauchin. And what you can see is that there are quite a number of cases that are possible now, quite a number of sample sizes. But if you're thinking of screening settings where you'd like to have a fairly large factor to run ratio, in many of these you're still pretty limited. So for example, with 80 runs, the best available result is 12 orthogonal factors. Okay? With 112 runs, best is 12. Okay? 96, you can get up to 24. So what I'd like to be able to do is to fill things in here that have, where we can get more sample sizes and keep a high factor to sample size ratio. Now, those of you who are here for Beauchin's talk, I hope came away with the impression that it's not easy to do that. So if you want to have Latin hypercube design and have perfect orthogonality, not a trivial task. And so what we're going to do is we're going to compromise slightly the Latin hypercube property. And that's why these are nearly Latin hypercube designs. What essentially defines the Latin hypercube? The fact that it has these absolutely perfectly spaced univariate projections. Well, we're going to give that up. Not by much, but we're going to give that up. And we're going to do that in order to maintain the bivariate orthogonality. Okay, so here are the basic ideas, and it comes out of this idea of rotated factorial designs. Okay, so this is work that goes back to my work with Dietze Burstein, as well as Dennis Lin's work with a student of his, Jim Beattie. And here's sort of the two basic ingredients to this. The first is that if you start with a standard first-order orthogonal design, and in particular we'll have in mind two-level fractional factorial designs as well as Plackett and Berman designs. So call that design D. Multiply that design by a rotation matrix R. So we have an n by p, an n by k design, okay, and rows by k factors. I'm going to multiply it by a k by k rotation matrix. Okay, what distinguishes a rotation matrix is that it transpose itself gives the identity matrix. Well, it's very easy to see that this new design that you got by rotating then preserves the orthogonality. So any rotation of an orthogonal design is going to keep you with an orthogonal design. Okay? Can you rotate into a Latin hypercube? And the answer is yes. And this is the result that Dennis and his student Beattie came up with. And then we're going to combine that with an idea for grouping columns that was in Dietze Burstein's dissertation. And we're going to show that that's how we're going to get these large Latin hypercube designs, orthogonal Latin hypercube designs. So here's the basic algorithm. Okay, if you take to rotate a 2 to the k factorial, and I'm thinking of a full 2 to the k factorial into a Latin hypercube design, what you want to do is this. Okay, so you think of the columns in a Latin hypercube design. What are they? Each of them is an arithmetic sequence. Okay. Take a look at what you get when you multiply D by this rotation matrix R. Well, any column in D times R is some linear combination of the rows of the rows of D. Okay, so I'm going to take a row of D. I'm going to take a linear combination of that row. That's going to give me an entry in the new column. Okay. Well, look at the rows of D. If you have a full 2-level factorial design, what I want to do is think of those 2 to the k points as a binary expansion of an odd integer. Okay? And then when you take all those binary expansions, you actually generate precisely an arithmetic sequence. Okay? And then, so we're just going to use appropriate powers of 2 in our matrix R. So the way it works, again, is very simple. So here you have a 2 to the cubed factorial design. I'm going to stick on weights, which are powers of 2. You can put the weights anywhere you want. You can put plus or minus signs on them. That's fine. And now I'm just going to compute those weighted averages of the rows, and there are the weighted sums. And you can see that what you get is exactly an arithmetic sequence of odd integers, just what you want for a Latin hypercube design. Okay, well, that's nice. I mean, you can generate one column like that. Now, can you generate a bunch of them using weights, which themselves, remember these weights are going to go in my matrix R, and I want that matrix to be a rotation matrix. Now the question is, can I find a rotation matrix like that? And the answer is yes, provided, and the provided is that R has to be itself a 2 to the m by 2 to the m matrix. So my R matrices are all going to be set up in terms with either 2 by 2 matrix, a 4 by 4 matrix, an 8 by 8 matrix, etc. And this was a work from Min and Beatty, and it's sort of based off starting with just a simple matrix. Here's the next matrix, R1, 1, 1, minus 2, minus 2. And what did I do? I took this matrix, put it here and here, and then put it here and here multiplied by 2. And the square root of 5 is just to normalize. And that's the pattern that we're going to follow all the way through. So whatever I had before, I'm going to put that on the diagonals. And then I'm going to multiply it by an appropriate power of 2, once with a plus and once with a minus. That's going to go on the off diagonals. One feature of this matrix, which will be relevant later, so keep it in mind, is that the highest powers of 2 are going to, in this matrix, the highest powers of 2 are going to run in 2 by 2 blocks down the anti-diagonal. Okay. Well, now how do you form a full design? That's nice if I have just one full factorial, k factors, and k is 2 to the m, and I want to get a new k factor design. How do I put together a larger design out of that? Well, the trick is simply to group the columns into groups. So for example, suppose R is an 8 by 8 matrix. I start with not a full factorial, but a fractional factorial, a saturated fractional factorial. I'm going to take the columns in that fractional factorial and break them up into groups of 8. Okay, and I'm going to break them up into groups of 8, rotate each one separately, and that's going to give me this large orthogonal Latin hypercube design. Can I break the columns up in a way so that all of them are full factorials? And the answer is yes. There are some nice results using Galois field theory that show you how to do this breakup, and that's what Dennis and I published in our earlier paper. Okay, so here you get an orthogonal Latin hypercube. Okay. In order for that to work, and in order to get that linear, that perfect sequence of odd integers, I had to start with a full factorial design. So when I hit some initial design D with that matrix R, the design that I'm hitting has to be a full factorial. What if I don't have a full factorial there? What if I have some nice collection of points from a full factorial set, but maybe not all of them? Well, I'm going to get, again, a rotated column. Everything, I'm going to keep all the orthogonality, as that's exactly what I want to do. I'm not going to have perfect spacing. I'm going to lose the Latin hypercube property. And that's exactly what we're now going to do to generate these orthogonal nearly Latin hypercube designs. Just as an example, suppose I start not with a full factorial, but with a 48-run Plackett-Berman design. I'm going to rotate this design in 5 sets of 8 columns each. I still have to take for each set, the number of columns still has to be a factor, a power of 2. So I'm going to take groups of 8. How am I going to divide up the 47 columns in the Plackett-Berman into 5 sets of 8? Good question. If anyone has some answers, I'd be pleased to hear. I don't know entirely how to do it yet, but I'll tell you a bit about it. Okay? So I'm going to get a set of 48 runs. And each one of those is going to come from one of the 48 rows in that projection of the Plackett-Berman onto 8 particular columns. Obviously, since I only start with 48 runs, I don't have a full 2 to the 8th factorial in any of those, so I'm not going to recreate everything. I'm not going to recreate a full sequence of integers. But for example, these are just some uniform QQ plots of 12 factors. I set up a 12-factor design with 48 runs. Here are uniform QQ plots. Yeah, there's some gaps there. There are some spots where these have little plateaus. Sometimes you might even have a repeat value. But remember, this is a repeat on one factor. I've never seen any problems where you have repeats in a two-dimensional projection. But you don't always get good two-dimensional projections. We'll get to that. Okay, so you're giving up a little bit in the perfect spacing, but not a whole lot with these designs. And you preserve, of course, perfect orthogonality. If you had a true Latin hypercube design, the univariate interpoint distances are all 0.043. For the design that I just set up, I pointed out there are some zeros. There are some repeat values on some factors. The largest distance that I happen to have ranged from 0.094 to 0.172. So, so looking from one factor to another, the one that had the shortest, longest distance, it was 0.094, and I got up to a distance of 0.17 between two successive points on one factor. Here are some two-factor projections of the design. I think they look overall pretty good. I mean, I don't think anyone would look at those and say, boy, this design is really awful. I think they look not bad. Okay, so what can you say about these properties? About the univariate and at least the bivariate properties. You can say things about higher projections, but I'm having enough trouble with these already, so I'm not going to go past that. Well, suppose you denote the columns of the Plackett-Berman itself, the original 48-run Plackett-Berman by C1 up to C47. Okay, how am I getting a new column? My new columns I'm getting by taking 8 of those, because I rotated in sets of 8. So I'm taking 8 of those columns, and I'm hitting them with powers of 2. That's how I'm getting all my linear combinations. So one of them is getting hit by 2 to the 7th, by 1 by 2 to the 6th, 2 to the 5th, 1 by 1, and there might be pluses or minuses on those. So that's how I'm setting up all the columns. Well, you can see that if you think of, is the point to this side of 0 or that side of 0, entirely determined by C1. So if C1 is 1 or minus 1 in the Plackett-Berman, that tells me whether or not I'm on this side of 0 or that side of 0. Okay? C2 tells me if I'm on to the left of 0, where am I relative to minus a half? So this is giving me halves, quadrants, octants, etc. So the top columns in here are the ones that really have the lead columns in terms of the powers of 2. Those are the ones that really dictate what's going on. And if you look at the projection of the Plackett-Berman onto those columns, you'll learn a lot about what's going on with the univariate properties of this design. We know for a Plackett-Berman that we have perfect, I've gone ahead or gone back? I'm going ahead. Okay. That we have perfect balance between C1 and C2, right? That's property of the Plackett-Berman. So we know that a quarter of the points are going to be in every quadrant for each univariate, for each of the new factors. Okay. So that's already some nice balance. If you want to know about the octants, you have to look at the projection onto three factors, and those tend not to be uniform for the Plackett-Berman designs. Okay. If you had a 3-factor projection, and this does happen sometimes, which actually has one of those doesn't occur, you might have an octant that has no points at all. And if you had a projection that on all 8 factors, if I'm rotating in sets of 8, if there's actually a repeat on that 8-factor, on those original 8 factors that I was rotating in the Plackett-Berman, I'm going to have a repeat value. And you saw that I had some of those. So repeats, even on 8-factor projections, can occur in Plackett-Berman designs. What if you look at pairs of columns to get bivariate properties? Same ideas. Okay? So here you have what's really going to dictate is C1, C2. That's going to give, for example, the quadrants for the first factor, R1. Here I have another factor, R2. Its highest columns are D1 and D2. So if you think of the bivariate properties, a lot is going to be dictated by the projection onto these 4 columns in the Plackett and Berman. Okay? So what can we say about those? also, if these two columns were formed from the same rotation set, okay, these are the same 8 columns but in a different order. And if they happen to be adjacent, remember what I said about those, how the highest powers of 2 were set up. If these happen to be adjacent columns, C1 will be D2 and D1 will be C2. And that can lead to some rather unpleasant looking two-factor projections, as we will see. The balance on C1 and D1 again guarantees that if you look at each quadrant in the in the 2x2 in the two-factor projection, you've got a quarter of the point. So you have what Beauchinte labeled the U design based on a 2-level orthogonal array. So we have some good properties already. If there's perfect balance in that 4-factor projection, 1/16 of the points are going to be in each of the squares in a 4x4 grid. But Plackett-Berman designs don't tend to have projections that look like that. Remember I talked about the adjacent columns. Well, here are 2 adjacent columns after you rotate. And when I said before the break that I'd used a design that I regretted afterwards, that was the 2-factor projection, essentially, in the 2 most important factors. And when I wanted to do some more detailed modeling on those factors, that was not very helpful. This is orthogonal. You can sort of see it's based around this sort of rotation of having sort of a center point here in each of those, which is a simple rotation, an orthogonal rotation. And then it's got points that sort of spread out around those. I'm not sure, Derek was mentioning the cascading Latin hypercubes, and I'm not sure if this is exactly how those look, but it does look similar. Okay. A little bit about 4-factor projections. What I know largely empirically. I haven't been able to prove a whole lot about this. I've spoken to some people who I think do know a lot more about this, and they haven't been able to tell me a great deal more about it. Anyone who does know, I'd be very interested to hear. This is for the 48-run Plackett-Berman design using the Paley construction. There are only 7 different 4-factor projection patterns. It's kind of interesting. So what you're looking at here is all the 4-factor projections. These ones that are most balanced have 3 points which are repeated 8 times each, 2 points which are repeated 4 times each, and 4 points which are repeated 4 times each. So when I said that usually you don't have perfectly balanced projections, none of them are perfectly balanced. There are no projections of that design which have 3 points each repeated 16, which have 16 points each repeated 3 times. None of them. And you do get some projections which, for example, down here, you have a couple projections where there are points which do not occur at all. But those don't occur, those aren't very frequent. Most of the projections are pretty uniform. Okay? So about 94% include all 16 points, and no projections, as I said, have 3 repeats of each run. How much you like to set up the rotation sets? Well, you'd like to get rotation sets that give you good 4-factor projections. Not so easy to do that. We don't have an algorithm that does this. And if anyone has some ideas for an algorithm, I'd be very interested in hearing about them. Ideally, again, what you'd like to do is you'd like the 2 leading columns for each of your new factors to give you a good 4-factor projection. So you have to get lots of good sets of 4 factors for this to work. I don't think I'm going to say a whole lot about this. Just to give you an idea that things are not as simple as that table that I just showed you for the 48-run design. If you go to the 52-run Plackett-Berman design, there are 400, this is the Williams construction, there are 425 different 4-factor projection patterns. Some of them occur for as few as 10 4-factor projections. Most of them include all 16 points, but some include only 12 of the 16. So some strange things can happen in these designs. So let me see what else I wanted to say about this. So I think I'm going to skip these things. Wait, but there was another slide that was supposed to be in here, and it got out. Oh, no, okay, I guess it was there. Okay. I was looking for that bad projection, but it was there. Okay. So one thing you might want to do is to look at, for example, minimizing the sum of squares of the repeat numbers to decide what's a good projection and so on. Again, even just classifying what's a good projection is not altogether trivial. And I'm going to say just a little bit about what are these designs good designs in any statistical sense? And we looked at this trying to build in some ideas of bias. So we're thinking of using these in a very simple screening setting where, say, you're fitting a first order regression model, but you think that there are more things around explaining what's going on, and you'd like to then look at how your estimates of the screening coefficients are being biased. So you want to look at properties of this matrix A. And in particular, we're looking at the sums of squares of those of that matrix. And just to give sort of a comparison, this is a comparison between design like I just showed. In this case, I took a 48-run 10-factor design, and 10 factors probably is too small here. So again, I'm thinking of these as being more useful in larger settings. And what I'm going to look at is just some quick results comparing this to a Latin hypercube design, and this one I took from the site at the University of Tilburg, for fitting first-order terms when actually that extra part includes second-order or pure cubics, or when you're fitting first and second order in this case, but you actually need pure first and second order, and you need all second and third order, and pure quartics. And if you compare the designs, I also computed the minimum distance for these. Okay, so this is a maxi-min Latin hypercube. It's guaranteed to give a minimum distance which is large. And this design is not all that far behind. Okay? And if you look at the bias results, the maxi-min design actually does better for case 1 that I presented, the maxi-min Latin hypercube design. When you get into case 2, where you want to include more terms, the orthogonal nearly Latin hypercube gives a better result. These are properties where, again, I don't know enough yet. We haven't looked at them in enough detail. I can't tell you a whole lot more about comparing the designs in terms of how well they do for modeling. So anyway, to conclude, rotations of standard designs I think, can give you some useful screening designs for computer models. The initial work that we've done suggests that they can be useful for identifying important factors, and although we don't have an algorithm for generating good rotation sets, it seems that most 4-factor projections, at least to the extent that we've looked at in Plackett-Berman designs, are not so bad. So even mating randomly may not be altogether a bad thing. And with that, I conclude. I will just add one comment, which I should have made at the start, and that's to give warm thanks to the organizers, to Tom and Angeli for inviting me to speak here, and for those who organized the entire program, Rosemary, Steve, Anthony, for the wonderful opportunity to spend time here.
Okay, any questions? Question?
In grouping the factors for rotation, for 48-run, you choose the group size 8. Do you have some guidelines for deciding on the size of group?
Yes. The groups have to be powers of 2. If you'd only, for example, with 48 runs, if you grouped in sizes of 4, then obviously you've only got 16 possible projections onto the 4 factors, so you're obviously going to have repeat values. You can't have any more than 16 different values. So you certainly want to go up to a power of 2 that's larger than, so 2 to the power of the number that you're rotating is going to be, should be larger than the size of than the number of runs. Would it be worthwhile to go up larger? I don't think you'll gain a whole lot from it, but you might. I mean, if you think about what you get by going up, in my example, I could have rotated, instead of rotating 5 sets of 8, I could have rotated 2 sets of 16 and 1 set of 8. That's also perfectly okay within the scheme. But if you think of what you're getting by, say, combining 2 sets of 8 into 1 set of 16, you're getting jitter at very small levels, because those are already designs that you've divided. The first 8 factors divide the points within, say, bins of width 1/2 to the 8th times the length of your interval. Okay, and the next ones are taking those 1/2 to the 8th bins and dividing those in half. So you're not going to be going from 8 to 16 in that case would not be varying the points by very much. If you were starting already with a large design, if you were starting with an 800 run a Plackett-Berman design, you had a large number of runs, you had a very large factor size, then I would expect that since 2 to the 8th is 256, then I would expect, yes, you probably would want to combine and work in sets of 16. But then, you know, sort of the rough guideline, I would just go up to whatever is the next higher power of 2 beyond the sample size.
And there's a bunch of goals here. You know, your first point, for instance. But if you're going to do screening and you're looking at a large number of variables in a small number of runs, you know, so this computer model's modeling reality, and in reality, if we were experimenting on reality, what we would do is probably a fractional factorial, like a Plackett-Berman design, and just say, who are the big guys, right? In terms of screening, have you just tried that and said, okay, well, I'm just going to do a QQ plot, half normal plot, because the things that are negligible probably are not 0, otherwise they would not have been included in the simulator. And you might be able to do that screening just like you would with physical data. I'm curious if you've tried that at all.
I think, you know, why would you prefer, for example, a design like this as opposed to just using the Plackett-Berman itself? I mean, that's sort of the heart of the question, right? And I think that the reason that a design like this might be preferable is you do the screening, you identify the most important factors. Will this be as good for identifying the most important factors? Open question, I don't know. The advantage of this sort of design for identifying important factors is because of the fact that at least univariate, it does give you a lot more levels for each factor. It gives you much more ability to detect dependence on those factors, which is not linear. Whereas the Plackett-Berman, being limited to the 2 levels, can only pick up that very simple sort of dependence. Second potential advantage is that you've done the screening, you've decided that there are only a modest number of factors that really seem to be doing things. This does let you fit more complex models to those in that reduced dimension. So I think there is some potential benefit here, and again, this is not sufficiently explored, but some potential benefit in being able not just to screen, but to then use those same data to do some more complex fitting.
Okay, so let's thank David again.